Alright guys, today we're going to talk about Graham's Law. You need to make sure you know Graham's Law. If you don't know it by now, make sure you write it down, because you're going to be using it for the next 4 problems. The speed of one compared to the other is the inverse of the square roots of their molar masses. Okay, so you need to know that. So let's go ahead and do this one. Assume the speed of a nitrogen gas molecule, that's good, there's only supposed to be one O in there, is molecule, how cool, is 1141 miles an hour at room temperature. What's the average speed of an oxygen molecule at the same temperature? All right. Well, remember what we have is our rate of A divided by our rate of B is equal to the square root of the molar mass of B divided by the molar mass of A. All right, so let's look at what we have. We're going to look at A as being oxygen and B as being nitrogen. So if A is oxygen, that's the one we don't know. We don't know how fast this is going. This is our unknown. We do know that the rate of B is given to us. It's 1141. So let's see. So the bottom here is 1141 miles per hour. And that's going to be equal to the molar mass of B, the square root of the molar mass of B over the square root of the molar mass of A. Well, A is oxygen, so that's going to be 32. And nitrogen is 14.007, so that's going to be 28.014. So if I take the square root, now this is again a math problem. To me it's just plug and chug. You take the square root of 28.0414, and you multiply that by 1141, which is your miles per hour, and you divide by the square root of 32. That's pretty simple. Then you come up with your answer. And your answer is going to be 1,068 miles per hour. So about 100 miles an hour, a little less, maybe 75 miles per hour, slower than nitrogen. Does that make sense? Well, oxygen's heavier. So since oxygen is heavier, it should be traveling slower to have the same kinetic energy. So that makes sense. Okay, let's go on to the next one. What happens if you have equal amounts of helium and argon and they're placed in a porous container and allowed to escape? Which gas will escape faster? And how much faster? We're talking about a fusion here. And again, we simply say the rate of one compared to the rate of the other is equal to the inverse of the square roots of their molar masses. Well, what do we know? Well, we can tell. We know helium. And what we're trying to do is we're trying to get, we assume that helium is going to be faster because it weighs less. So we're going to put helium up here and argon down here. So that means we need the molar mass of argon on top. So the square root of, let's say, argon is going to be 39.948. I looked that up on my periodic table. And the molar mass of helium, which is 4.003, I take the square roots of those things and divide, and I get 3.16. So that tells me that helium is 3.16 times faster than argon, simply based on their molar masses. That's pretty cool. All right. What is the molar mass, or the molar weight, a molecular weight of a gas which diffuses 1/5 as fast as hydrogen? Right, well, let's do our rates again. The rate, let's say that's hydrogen, compared to the rate of my unknown, is equal to, well, the molar mass of hydrogen, the square root of the molar mass of hydrogen, divided by the square root of the molar mass of my unknown. This is what I'm trying to calculate. All right. So what do I know about the rates of these two things? Well, I'm told that that the rate of hydrogen is 5 times faster than the rate of hydrogen is 5 times faster than the rate of my unknown. Okay, so that means that if I take the molar mass of hydrogen, the square root of the molar mass of hydrogen, doing this right, the rate of hydrogen is 5 times faster than the rate of my unknown. That means I have this upside down. I knew something didn't look right. All right, the rate of my unknown is 1/5 the speed, so it takes 5 times longer for that to happen. Good, so that makes more sense. All right, so I take 5 times the square root of the molar mass of hydrogen. Now, the molar mass of hydrogen is 2.016. Right, so if I take the square root of 2.016, multiply it by 5, I come up with, and then I have to take, this is going to be equal to the square root of the molar mass of my unknown. So that means I have to take this entire thing over here, and I have to square it, and that will get rid of the square root sign, which means that will give me the molar mass of my unknown. So now if I plug this into my calculator, right, this number, let's do it in stages. If I have 5 times the square root of 2.016, right, that's going to give me 7.099. But because I'm under a radical sign here, I have to square this thing. So if I multiply it by itself, so if I square 7.099, I get 50.4, which is the mass of a gas that would be 5 times or 1/5 as fast as hydrogen. All right, let's look at number 4. Number 4 is very similar to the last one, except this time we're not calculating something under the radical sign. What we're trying to do here is we're saying the rate of hydrogen compared to the rate, of sulfur dioxide, and that's going to be equal to the square root of the molar mass of sulfur dioxide divided by the square root of the molar mass of hydrogen. Okay, well, what's the molar mass of sulfur dioxide? Well, I had figured out sulfur is 32.066, and oxygen, there are 2 of them, so that's 32. So my molar mass is going to be 64.06. All right, so the number going in here is 64.06. The number going in here for the molar mass of hydrogen, we just calculated that in our last problem, which is 2.016. So we take the square root of the top, divide by the square root of the bottom. Now, what are we doing over here? We're saying how much faster does hydrogen escape through a porous container? So all we have to do is divide those things, and that thing is going to be equal to 5.637. So that tells me that hydrogen is 5.637 times faster than the rate of hydrogen. It's going to be 5.63 times faster than the rate of sulfur dioxide. Well, gee, that kind of makes sense because we just looked at, in our last problem, we just said that something that weighed 50 grams would be 1/5 as fast. Well, this is between 1/5 and 1/6, and it weighs a little bit more. So that kind of all fits together and makes sense. Okay? All right. I think that's it for Graham's Law. And if you have questions, come see us in class. We'll be happy to answer them. See you then.